Okay, and then we are going to share. Okay, let's take a look at the syllabus and the schedule. We are writing here. Let's see if we finish mirrors. We didn't finish mirrors, right? Let's take a look if we finish mirrors. Yeah, look, we finished mirrors. We did concave mirrors and we did convex mirrors. Okay, and insert age break. Today is May 7th, 25, week number 13. Right? Let's see, the exam is going to be in 2 weeks. This third exam is going to be in 2 weeks. And we are now getting into, yeah, we don't need mirrors anymore, right? Wait a minute. Here you go. This one is, okay, so we finished mirrors and now we're going to start refraction 1, refraction in lab 6, right? First hour we lecture, the remaining we do the so-called lab. 2 weeks from now is the 30 exam. Then we have a Memorial. Let's make sure we have a Memorial Day. I don't want to, we're gonna have a holiday soon after, right? Let's make sure that I got the right date this time, so I don't keep announcing holidays that don't exist. Spring calendar. Okay, let's see. I will have to go elsewhere. I can't find here. LA Harbor College. Academics. Schedule and catalog. Fall. Spring. Right in here. Holiday. Monday, May 26. Right, let's go back there. Monday, May 26. That's good. So we have the exam is just before the holiday. Okay. If you want, we may, right? We may do this exam soon after the holiday. Think about that if you prefer to do that. The advantage is that you'll be doing the exam after the holiday. The disadvantage is that the third exam will be 1 week before the final, right? So think about that if you want. What do you prefer? What do you prefer? Okay, either the 21st of May or the 28th of May. Let's write it down. Okay, so week number 13, meeting number. Let's go back here. Meeting number 21. So one, I corrected lab 3 and posted its correction in Canvas. Okay. I noticed that many of you did not do anything in the spreadsheet, did not do anything in the spreadsheet. Okay, those who did not do anything got a 20% grade. Okay, let me know if you were one of them, if you're one of them, if you are one of them, let me know what's your difficulty. I know that many of you did not do anything in the spreadsheet, both lab for lab 3 and 4, for labs 3 and 4, okay? Those who did not do anything got 20% grade. If you are one of them, let please let me know. Please let me know why you didn't, why you did not complete the spreadsheet, okay? I thought my supposed to say, say, okay, so here we go. Yeah, just so let's talk about that after the break, okay? Let's talk about that after the break, and now what else we need here? Go to the
Professor, I have a quick question.
yeah. Go ahead.
When we submit the report, I don't know if this happens to anybody else, but when you give us access to it, it it I think it counts as a submission. So, for example, when I got access to lab 4, there's
Uh-huh.
a blank there's a blank spreadsheet and then there's the one that I submitted.
Okay. Are you talking about lab 4?
Well, it happens with all of them. So as
Uh-huh.
soon as I like click to download the file, it like counts as a submission.
Really? Well, it's
So
I,
I
mhm,
resubmit, but usually on my submissions, there's usually two. It's the blank one and then the one where I did the work.
really?
Yeah.
Okay. Okay. When I download the yeah, when I download the spreadsheets, I got, let's say, half of the students. I got half of the students with the corrected submission. Okay. So maybe there's something wrong with Canvas. I'm gonna give you another chance for Lab 3 and Lab 4. Let's do this way. I already gave you a chance to submit Lab 4, right? So I'm gonna give you another window for Lab 3, and let's see if it goes through this time. Let's do this way. Okay?
Okay. But if there is two of them, are you looking at both of them to see which one has
Oh,
the
oh,
work
when
on it?
when I download it, it shows just one per student. Okay? When I download from Canvas, it shows just one spreadsheet per student. That's what it does. It doesn't download two spreadsheets per student. Okay.
Yeah,
That
but is there a chance that the one you downloaded for some people are the blank ones? And that's why?
I do not know. That's a good question, right? Well, we have to inquire with Canvas. I will ask them, and let's see if it's a problem with Canvas or if it's something that I'm doing that I'm not doing correctly when I download it. Okay, I will inquire that with Canvas. It's really, it's really sad because when I saw those spreadsheets, like I have only half of the students that completed the spreadsheet, and and maybe it's a problem there with Canvas. I will inquire with Canvas. Let's see. And at the same time, ask Canvas too about that. If you can ask Canvas, you can explain what happened to you.
Well, I mean, for example, if you look at my lab number 5. I still haven't submitted my work, but
Uh-huh.
there's one there that's already submitted,
Okay. That
and it's
is there
a
is one
blank.
that's one that is already submitted because I uploaded it, right?
Okay.
Yeah, I believe that's because I uploaded it.
Yeah,
Yeah.
and it counted as an attempt. I just wanted to let you know.
Yeah, okay, that's nice to know. Yeah, I was suspecting that there was something wrong with Canvas, but I will confirm that with the Canvas support, okay? And again, I'm going to give you a little bit more of time. I'm going to extend Lab 3 deadline, okay? Lab 4 deadline is already extended. Is I believe it's just a matter of uploading whatever you have already completed, right, for Lab 3. Is that right, Ramon?
Lab 3 I didn't get access to because I missed that day.
Okay.
So that one is I don't have that one, but I'm talking about for all of the other labs.
Oh, you're talking about Lab 4
Yeah,
as well?
lab 4 or
Uh-huh.
lab 4 and 5, you'll see
Okay.
both the blank one, and then for lab 5 you'll see just the blank one because I haven't submitted the edited one.
Okay. Okay, but you did submit Lab 4, right?
Yes.
You did submit. Okay, I will. And Justus, did you submit Lab 4, by the way? No, you didn't. Okay, good. Okay, and did you submit Lab 3? That's for Justus again. Yes, but when I checked my submission, yeah, go ahead, finish. Huh. Okay. Okay, I will, when the class is over, I will give a call to the Canvas support, see if there's something wrong there with the Canvas, all right? And I will also extend the deadline of Lab 3, give you another opportunity, okay, to submit it. And okay, so let's here is I don't want that set aside. Okay, one more. I'm gonna close this one. Okay. I noticed that many of you did not do anything in the spreadsheet. Okay, lab 3. Okay, I will give an opportunity to submit lab 3 again, and I will check with Canvas support. There's there's a problem with the Canvas submission process. Okay, so okay, and let's go back. Let's go back to the book. Here, reflection of light, right? Formation of image by a plane mirror, and spherical mirrors, both concave and convex. Don't forget we are doing only concave, only spherical mirrors, which is the simplest of our mirrors to be treated. And again, the concave mirror, the spherical mirror is not the ideal mirror, but it's still useful. It's not the ideal mirror because it doesn't focus all the light in a single place. Okay? If you get a very large uh, radius of curvature for your concave mirror, for your spherical, not just for the concave mirror, but for the spherical mirror in general, not all light rays are going to be focused at half the distance, okay, of the circumference of the radius of circumference of the mirror. So the ideal mirror to do something like that, to focus all the light at a single point, is the parabolic mirror. But the parabolic mirror is far more difficult to manufacture, to grind it, okay, than the spherical mirror. I myself, when I was a kid, I managed to create a spherical mirror, okay, and it worked very well. I was doing a telescope mirror here in Brazil, and I managed to create this mirror. It just was of work. But nowadays we don't do that by hand anymore. We just hire an industry or buy off the shelf stuff. So I'm gonna write that. That's what this illustration is all about. Okay, that's how a spherical mirror behaves. However, if you get a very small slice of this spherical mirror, you will be able to get a very good spherical mirror that focus most of the light at the focal point. Okay. The problem is that when you start to get such a large mirror and a very small, not large, but it's very small radius of curvature, that's when the focusing problem starts to happen. Okay? And in order to correct this problem, you will have to use a parabolic mirror instead. The surface is parabolic. It's a parabolic surface, not a spherical surface. Okay? Parabolic, exactly what we learn in math, right? When I mean parabolic surface, I mean exactly that. It means that the equation for this curvature is proportional to x squared. Okay, proportional to x squared. Okay, so we can write or even r squared if you're using not this kind of this is a cylindrical parabolic mirror because there is no curvature along this line. Okay, there is a curvature only along this line. But if you're going to build a telescope, okay, you will have a curvature, parabolic curvature along this line, and another parabolic curvature along this distance. Okay, but those solar collectors, they don't need to be like a parabolic mirror that you use for astronomy, for imaging distant objects. That's what I want you to understand. Okay, see, long row of parabolic mirrors, and let me write that down as a. Just keep in mind, right, that we studied spherical mirrors only. Okay? Okay. Spherical mirrors are easy to manufacture, are easier, easier to manufacture, but they are not the ideal mirrors, ideal type of mirror. For use. Why is that? For use because if their curvature becomes small enough, but it has to be small enough compared to something else, right? And this something else compared to the size of the mirror, okay, comma, not all the light of the mirror will be focused at the same point, okay? Although we have this problem with spherical mirrors, comma, this problem is minimized. This problem is minimized when the diameter of the mirror is much smaller than the radius of circumference of the spherical mirror. That's what C is all about. Radius of curvature, not radius of circumference, okay? Where D stands for diameter and C stands for radius of curvature of the mirror, comma. In order to correct this problem, okay? And this problem has a name, let's see. Okay, so that's the problem here, right? With the spherical mirror, see? The mirror is not focusing all the light in the same point. But if we restrict the light rays only to this region, up to this region, right? Most of the light will be very would be very close to the focal point. Very close to the focal point, okay? Okay, to resolve this problem, in order to correct this problem, we use instead parabolic mirrors, which are capable of focusing all the light into a single point, okay? So that's how they build the telescopes. Most reflection telescopes are built with a parabolic mirror. Okay. Okay, so let's see what else we have here that I want to pass to you. That was something that I didn't understand as a student. I didn't quite, understand as a student. But now, I want you to understand, okay? Pass that to you. And formation of images, okay? And I covered that as well. Concave mirror between the focal point and the mirror, right? And convex mirrors. Convex mirrors are simpler than the concave mirror to deal with. Here's the equation, okay, that I passed to you. One equation, another equation, another equation. Magnification, here we go. This equation, and this equation here. Those three equations. Here's the James Webb Space Telescope. It's amazing how large we can make mirrors nowadays, okay? It's really amazing. When I was growing up, the largest telescope in the world was that telescope nearby San Diego. I do not know if you have been there, in Mount Palomar. I went there several times. It's a really nice place. I like that place. I once flew, I once rented an airplane, a small airplane, and flew from Torrance to Salton Sea Lake. And along the way, we passed nearby Mount Palomar, and I could see that huge dome of the telescope, which at the time, several years later, let's say 40 years ago, right? 40 years ago was when 1980s. At that time, 1970s, 1980s, Mount Palomar, the telescope in Mount Palomar, the Hale telescope, we call it, was the largest telescope in the world, 5 meters diameter. 5 meters diameter at that time. Later on, the Russians built a larger mirror, 6 meter diameter, but it has so many problems that it didn't work as well as the Mount Palomar telescope. Okay. Nowadays, we're building mirrors that are 30 meters diameter. Okay. And even let's take a look at this one here. Physics of searching for extraterrestrial. This one here is the optical telescope primary mirror. the James Webb Space Telescope. I want to know the diameter of this telescope here. Secondary, he's talking about the secondary mirror. Oh no, it's 7.32 meters from the primary mirror. But he doesn't say what's the diameter of this mirror. Does it say? The radius of curvature is 15.8 meters. Consequently, the focal length. Yeah, I don't see. Okay, 18 hexagonal, 1.3 meters diameter. 1. Okay, it's composed of an array of 18 hexagonal mirrors that are each 1.3 in width, not a diameter. Okay, overall diameter of the primary mirror is 6.5 meters. Okay, larger than Mount Palomar telescope, making the overall diameter of the primary mirror 6.5 meters. So it's larger than Mount Palomar, but then we have larger telescopes. Let's take a look out there in the internet. It's far more difficult to launch larger telescopes in space, right? So the largest telescopes are here on ground. The largest telescopes in the world. Let's take a look. List of largest optical reflecting telescopes. Wikipedia. Okay. Let's see. Grand Telescope in the Canarias. I believe this one in Chile, right? Yeah, no, in Canary Island. Okay. La Palma, Canary Island. 10 meters diameter. 10 meters diameter. Keck Observatory. That's in Hawaii. Yeah, Mauna Kea, in the west state of Hawaii. 13, let's see, 13,000, 10 meters diameter. Okay, so compare that to the Mount Palomar, right? That we used to have 5 meters only. Now we can build telescope there twice the diameter. And when we are talking about twice the diameter, the power of the telescope compared to the Mount Palomar is not twice the power. It's actually 4 times because it goes up with the area of the mirror, okay? Twice the diameter of the mirror, we have 4 times more capability. Goes with the square of the ratio of the telescope. So think about that. We're able in the last 40 years to build telescopes that are at least 4 times more powerful than the Mount Palomar telescope. And when I mean at least, I mean it, because it's not just the power of the telescope doesn't go just with the diameter of the mirror. You also have to consider that nowadays we have far better detectors than we used to have 40 years ago. Okay? Think about that. It's not just the size of the mirror, it's also the technology. And in 40 years, we got lots of things. You know, the technology just went. Man, it's crazy what we have nowadays compared to what we had 40 years ago. Back in the 1990s, when I was working at NASA, I couldn't get my experiments done with my optical fibers. I couldn't get it because we didn't have technology for that. But then as time went by, people start to invent other things, put in the market, for instance, detectors. You know, back at the time, I had to buy detectors that used to cost $3,000 at that time when I was working at NASA. Nowadays, I can buy a photo detector that costs like less than $2. You know, we are talking about 1,000, 3 orders of magnitude cheaper. And it also works much better, my photo detector that I work nowadays. And on the top of that, I also shrank the size of my devices. So when we are talking about telescopes, for instance, it's not just the size of the mirror that counts, but also everything else that coupled into this telescope, like the photo detectors, the cameras, okay, CCD arrays that we have nowadays. It's really amazing how technology advances. You know that technology advances in an exponential fashion. Okay, it's not in a linear fashion. It's not even with the square of the power. It actually advances exponentially. Let's see the Subaru telescope, where it is located in Japan. Okay, that's 8 meters diameter, right? Oh, but wait a minute. National Astronomical Observatory of Japan is located in Mauna Kea. Okay, people love to install telescopes there in Hawaii. Okay, people love to install telescope because why is that? because it's not just because of the large mountains or because it's isolated in the Pacific, but it's also because that those islands, they are very astronomer friendly. Very astronomer friendly. What does it mean, very astronomer friendly? Oh, it's just like that Palos Verdes, right? If you go to Palos Verdes, you do not have those mercury lamps that are very strong and bright and that illuminates everything. Instead, you have another type of light that's yellowish, okay, and another type of lamp that's yellowish. It's sodium lamp, and there in Palos Verdes we have those sodium lamps, but in most of LA County we have the regular mercury lamps. Okay, sodium lamps is better for astronomers because you can filter out the light of the sodium lamp using appropriate filters. And those guys that live in Palos Verdes, they're well-off people, and they were able to convince the city to install only sodium vapor lamps, so they could play with their own private telescopes there in Palos Verdes. Okay, it's the same thing in Hawaii. In Hawaii, people are very astronomer friendly, and the cities nearby they all use that yellowish sodium vapor lamp. And astronomers, when they install telescopes, if they want to filter out all that light noise that comes from the cities, the surrounding cities, all they have to do is to install a little filter in the telescope to get good images. Okay, so that's the Subaru telescope. We also have this neat type of telescope, is a binocular type of telescope, which is a rather different type of technology. I have seen something like that. I have visited there in a telescope like that, binocular telescope in Albuquerque, okay, which belongs to that Air Force base that they have in there. Okay. Now let's take a look at this one here. Another 10-meter telescope, McDonald Observatory in Davis Mountain, Texas. The large binocular telescope. Let's see what's the diameter of those. They don't say what the diameter of those telescopes. Let's see. Let's take a look here. When using both, okay, 8.4 wide mirrors, okay, and they are 14.4 meters apart, okay. So why they use double telescopes? There's a reason for that. It's a different type of technology. It's a little bit more difficult to understand, okay. When you place two telescopes next to each other at a distance of 14 meters, okay, 14.4 meters, you actually get the job of a 14-meter diameter telescope, not a 1.8.4, okay? The telescope can resolve stars with the power of a 14.4-meter telescope. That's what we call optical interferometry. It's far more complicated than the single mirror telescope, and it requires a far more precise alignment of the mirrors to do something like that. Okay. So there in Albuquerque, you have one of those binocular telescope. I managed to visit them when I was working there at the Phillips Research Laboratory. Very large telescope. Let's see this one here. Very large telescope, an astronomical facility operated since 1998 in Atacama Desert in Chile. They have very good places there too, very nice observatories. It consists of 4 individual telescopes, each equipped with a primary mirror that measures 8.2 meters in diameter. Okay, these optical telescopes, most likely they are also interferometric telescope. They don't say interferometric, but they should say that. Angular resolution, right? That measure these optical telescopes are generally used separately, but can be combined, okay, can be combined to achieve a high angular resolution. When they say they can be combined, it means that those telescopes are telescopes that use optical interferometry. Okay, so those 4 telescopes work just like those 2 binocular, just like that binocular telescope that you saw before. Okay, and we have something like that too in Mount Wilson, nearby Pasadena, right? If you can visit Mount Wilson, they have the telescope there in Mount Wilson, the famous telescope that Edwin Hubble worked on, but they are also installing those types of interferometric telescopes there in Mount Wilson. It's really nice. I visited their facility there as well. Those guys that work at those interferometric telescopes. Let's go back here, and very large. That's the interferometric. Southern African Large Telescope, 9.2 meters. Gemini Observatory. This one is in Hawaii and Chile, respectively. Okay, 8.1 meters. These twin telescopes offer extensive coverage of the northern and southern skies and rank among the most advanced optical infrared telescopes. Gemini Observatory, okay, one in Hawaii, the other one in Chile. Okay, what 369, 9 telescopes, greater than 8 meters. Okay, so now we can go back to our, and those are all reflecting telescopes. They all use mirrors, not lenses. Okay, we use instead parabolic mirrors, which are capable of focusing all the light into a single point. Most reflection telescopes are built with a parabolic mirror. Okay, so now let's go to chapter 26, refraction. Okay, right in here. I want to go down. I'm gonna click here. No, click here. 26, refraction of light. Okay, lenses and optical instruments. Okay, so here we go. So one of the laws of optics is the principle of least time. Okay, principle of least time. But another law is that light behaves like rays. Okay, but one of the laws of geometric optics, let's write it down, laws of geometric optics. The principle of least time. The principle that light behaves like rays. And there is one more law of optics or geometric optics, okay? That is a parameter that's called optical density of a medium, okay? And the name optical density is a very fitting name, okay? This parameter describes how fast is light slow light travels in a given medium, okay? And this parameter is quantified by a quantity that we call the index of refraction. You have to understand this idea of the index of refraction. Again, index of refraction is a measure of the optical density of a medium. The denser the medium, the slower light travels. The slower light travels. Okay. Okay, so can you think in terms of that? It makes sense, right? If the denser a medium is, the slower light travels. Similarly, right? The denser a medium is, the slower we will be able to go through that medium, right? It's far more difficult to move through water than through air, right? Because water is denser than air. Okay? So I think the name optical density is a very fitting definition. Okay. Now let's see what's the definition. What is the definition of refractive index, right? Refractive index or index of refraction. The definition is very simple. Index of refraction. We can measure index of refraction in the lab with certain materials. Okay, index of refraction can be index of refraction can be measured with a refractometer. I have already worked with something like that. Let's take a look in the refractometers. Portable digital refractometers. Okay. And instruments. Here we go. Let's take a look here. I love Wikipedia. I think they're very useful. See, a refractometer is a laboratory or field device for the measurement of an index of refraction. The index of refraction is calculated from the observed refraction angle using Snell's law. We're going to cover Snell's law, which is not a law, okay? It's just a law between quotes. That's a small device, but they have larger too. Benchtop device, there's a handheld refractometer. Okay, and okay, they use these devices, for instance, to check for the sweetness of fruits. Okay, the sweeter the fruit is, like an apple or a grape, the sweeter the fruit is, the higher the index of refraction of the fruit. Okay, so now what's the definition of index of refraction? Let me get that for you. We represent the index of refraction by the letter N. N for Nancy. Okay, is going to be given by the velocity of the light in vacuum, 300,000 kilometers per second, divided by the velocity of the light in the medium. That's how we define index of refraction. Can you remember that? That's not difficult, right? If you know, the refractive index of the medium, you can find out what's going to be the speed of the light in that medium. Okay? So from this definition, it is straightforward. It is straightforward to see that the refractive index of vacuum is 1, right? Why is that? Well, because lights travel in the vacuum at speed equal to the speed of the light. So if you're talking about vacuum, I'm going to put it here, vacuum. Okay? What you're going to have here, the speed of the light in vacuum is going to be c. C cancels with c. Consequently, we get 1. And then there are all other sorts of mediums, okay, that we can find out either the refractive index or the velocity of the light in the medium instead of vacuum. Okay, what about the refractive index of air? The refractive index of air, light travels in the air at almost the same speed in the vacuum. Okay, so I can write that down. It's not exactly, it's a little bit less. Okay, so I can say that the refractive index in the air is approximately 1, 2. It's not exactly, it's a little bit more than 1. We can even check Wikipedia, refractive, or even the internet. Here you go, refractive index of air. Because air is a denser medium, optical medium than the vacuum, right? The refractive, the speed of the light in the medium would be, the speed of the light in the medium would be slower compared to that in the vacuum. Look at the refractive index, 1.0003. For all practical purposes, refractive index of the air is 1. Okay? For all practical purposes. Okay. So for all practical purposes, the refractive index of the air is also 1. However, strictly speaking, index is a little bit higher. That's going to be 1, strictly speaking, right? It's going to be 1.000. Oops. How many zeros do we have? 1, 2, 3. Okay. 0.003. Strictly speaking, that's the refractive index of air. It's very difficult to measure something like that compared. It's very difficult to, to see the difference between the refractive index of the air with the refractive index of the vacuum. Other materials, other substances, other optical substances have the following refractive index. Water, 1.33. Can you remember that? Let's take a look. Refractive index of different substances, right? Different substances. Water is 1.333. Oh, 333. Okay. 1.333. Let me put another. Most glasses has a refractive index of approximately 1.5, depending on the glass. It varies anywhere between 1.4 to 1.6, okay? But most, you can see here, glass 1.52, see that? And look at diamond. Diamond has a very high refractive index, 2.42. Diamond, 2.42. Let's see if we have vacuum, air, water, glass, diamond. Another type of glass, crown glass, 152, flint glass, light flint glass. See, 1.6. Sapphire. Have you ever worked with sapphire? We have optical fibers, sapphire optical fibers out there. Let me put the sapphire right in here. Sapphire, 1.77, right? Yeah. Then you have all the other substances. Zircon, rutile, gallium phosphide. Depending on the sapphire here, has a range of refractive index. right? Boron nitride, cubic zirconia, and so on. List of refractive index, you can go to Wikipedia too and find out the different index of refraction that we have out there. Carbon dioxide, okay, has a slightly higher refractive index than air itself. Okay, helium, hydrogen, arsenium 3 sulfide, that's a liquid, 1.9. Carbon disulfide, benzene, 1.5. Carbon tetrachloride, kerosene, water, acetone. You don't have to memorize that, but you have to know the ballpark of the refractive index of substances, okay? Solids, 2.65 for silicon carbide. Other materials, Teflon, 1.31 refractive index. Cryolite, lever has a refractive index as well, huh? 1.369. The human lens has a refractive index between 1.38 to 1.40. Human cornea, this is slightly transparent, medium, right? 137, 1380, 1401. And sugar solutions, okay? If you vary the amount of sugar in water, you can get different indexes of refraction. 1.42, okay? That's why they put 50% here. 50% of sugar in water. Glycerol, 75% of sugar. Let's see, let's compare. 1.4774 compared to 1.42, right? The higher the concentration of sugar, the higher the refractive index. Can you remember that? PET-G, polyethylene, 157, and so on. Germanium, 4.05. It has a very high refractive index, germanium. And let's go back. And so on, right? And so on. I'm going to copy and paste this section here. I'm going to put right in here. Okay, index of refraction. We covered index of refraction. Okay, and now let's talk about Snell's law. Okay, so now you saw, now you understand, that light, now you know, right? That light travels at different speeds in different media. This effect, this characteristic result in rather interesting behavior, types of behavior, okay? So let's not forget, reflection is one thing, right? is different from refraction. Okay, what's the difference between one and the other? Reflection, lights bounce back from the surface, right? Refraction, light enters a different medium, okay? It doesn't bounce back, but just manage to enter a different medium. Okay, because, you know, when light enters a medium of different refractive index, comma, it may change its direction of propagation, okay? That's what you have to know about refraction. Let's go. The best way to understand that is to look at the drawings. We're done here. Yep. Now we are writing here. Here you go. Light travel in straight lines, right? From S to C, S to A, S to B. That's one of the postulates of geometric optics. Okay? If the medium is homogeneous, light is going to travel in a straight line. However, if the medium is not homogeneous like this one, here you go, you have one medium at the left and you have another medium at the right. Light is still going to travel in a straight line, but up to a certain point, okay? So if you light is gonna, here you go, let's go back here, right? See, CAB, right? CAB point, let's see here. That was, let me do something else here. Ah, man, sorry. Let's get this one here. Now, make it nicer, right? Homogeneous medium, right? When you introduce a second medium in the way of those, in the way of this light, the path of the light, you know, light is going to travel in a different way. Okay? It will no longer be in a single straight path. It's going to be in multiple straight paths. Okay? This is the path of least space, right? But this path of least time is going to be something like that. Okay? Light is traveling here 300,000 kilometers per second, and when it reaches this interface, what happens? It slows down. It slows down to something that depends on the refractive index of the substance. If the substance is glass, the speed of the light in the medium is going to be 300,000 kilometers per second divided by 1.5, which ends up being 200,000 kilometers per second. Okay? It's going to end up being 200,000 kilometers per second. Do you get the idea? And what else do you have to know? Let's see if I have the drawing here. Here you go. For point A, is something like that too. Okay? Light, and it all, every time that light goes from a lower refractive index, from a medium of lower refractive index to a medium of higher refractive index, the path of the light tends to move towards the normal. Okay? Do you see here? That's what we have here. This angle here, this angle of refraction here is lower than the angle of incidence. Okay? Same thing here. The angle of refraction right in here is less than the angle of incident here. Why is that? Because the medium, this medium here, the second medium, has a higher refractive index compared to the other one, the other medium. It's possible to prove that using the principle of least time. And here, now if light goes from a medium of higher refractive index to a medium of lower refractive index, the exact opposite happens, okay? Light moves away from the normal. And that again can be proven with the principle of least time. Okay, so let's talk about that before we get into this other topic. So here you go. Let's document here, right? If light travels from a medium of lower refractive index with medium of higher refractive index, comma, light changes its direction towards the normal. Changes its direction to an angle, to a lower angle in relation to the normal, with respect to the normal, okay? With respect to the normal, like that. Mathematically speaking, right? Here you go. Mathematically speaking is like that. I'm going to, if, in other words, if, if N1 is less, first medium, than N2, oops, what does it imply? This implies that consider, okay, let us say that light travels from medium 1 to medium 2, right? If N1 less than N2, this implies that the angle of incidence of the light at the interface, right, is gonna be greater than the angle of refraction. And I'm gonna put R prime so we don't, oh, no, I didn't work. Let's see. Now I can put prime here. Here you go. R prime means refraction. Oh gosh, not reflection, okay? Likewise, if N1 greater than N2, then the angle of incidence is going to be less than the angle of refraction. Okay? All of that is spelled out. All of that is spelled out in Snell's, I'm going to put it here, law, between quotes. And it's very easy. It's very easy to memorize this law. Okay? But first, I want you to remember, be reminded, right? First, be reminded of the law of reflection, right? What's the law of reflection? That angle of incidence is equal. Now I'm going to put the reflection just as R, equal to the angle of reflection. Be reminded of the law of reflection. All of that is spelled out. Let me see. I'm going to change the order here. All of this is spelled out in Snell's law. How is Snell's law? Snell's law is very easy to memorize. Okay. N1 times sine of theta incidence, right, is equal to N2 sine of theta of refraction. Can you remember that? Be reminded of the law of reflection and compare how these two laws are different. Okay, and I'm gonna insist in using quotation here in the word law. What time is that? Let's see here. It's time for our break, right? Otherwise, we're going to get burned out here. Let me adjust my time zone. Pacific. Here you go. 10:49. Let's take attendance. 7th of May. Abir Ahmad, are you there?
Yes, I'm here.
Thank you. Nestor Alvarado.
Up here.
Thank you. Monte.
Here.
Okay. Isabella Ballesteros.
Here.
Thank you. Justus Bowden. Hello, Justus. I'm gonna put a star here on Alexandra.
I'm here.
Okay. Your last name is Bermistrova, right?
No, I changed it recently.
Oh, you changed it. That's why. I was wondering
Yeah.
if we had a Romanov here and it wasn't here before, right? So you changed it from Bermistrova to Romanov?
Yeah, that's correct.
Ah, okay. So let me put it here, Romanov. I was confused last time, did I miss anything here? Romanov. Romanov, is that right, Alexandra? Romanov with F?
Yeah, Romanov
Okay.
with a V at the end.
The V, okay. So I presume you got married, right? That's why you changed your name. Okay. Benjamin Carvajal. Oh, Justus is here, right? Benjamin, are you there? Benjamin, I see Benjamin there. I'm going to put a star here under his name. Next, Elizabeth Castellano. Natalia Cordoba. You go. So hang in there, Natalia. Elizabeth, is she there? Elizabeth.
Here.
Okay, thank you. Natalia already answered. Jacqueline Delgadillo.
Here.
Thank you. Jenny Diaz.
Here.
Thank you. Valerie Diaz.
Here.
Thank you. Juan Escalera. I thought Juan was here. No, he's not here. He's not here. Let's see. No, he's not here. Bianca Eloki. Bianca not here. Next, Edwin Gonzalez. Next, Eli Gonzalez.
Here.
Thank you. Manuel Hernandez Pineda. Thank you, Manuel. Samantha.
Here.
Thank you. CJ. I don't see CJ here. Amber Lopez. Thank you. Adeli Lopez. Okay, I'm gonna put a star here under Adeli name. Genesis.
I'm here.
Thank you, Genesis. Mary. Thank you. Galia. Thank you. Ramon. Ramon is here, right?
Here, yeah.
Okay, thank you. Taylor.
I'm here.
Okay, thank you. Next, Jeremy Pittman. I don't see Jeremy here. Next, Stephanie Ramos. Thank you. Leslie Rios.
Here.
Thank you. Jason Strait.
Here, Professor.
Next is Hema Torres Navarro.
I'm here.
Thank you. And we have how many students? 25, 26, 27. Okay, good. Benjamin, are you there? Want to give you another chance here? Oh, yeah, okay. Thank you, Benjamin. And the other student is Areli. Are you there, Areli?
Yes, I'm here.
Okay, thank you. Now we have 27. Good. So is not what I want this one here. Is 10:55 a.m. to 11:10 a.m. break. Okay, so I see you in 15 minutes. Okay, I'm back here. Okay, so this equation has some rather interesting consequences. Okay, so like I mentioned to you before, just just think what can be an interesting consequence of this type of path of the light, okay? Going from a refractive index, the higher refractive index to a lower refractive index. It has a rather very interesting consequence. Not the other way around. The other way around is straightforward, right? Nothing very special other than, changing the path towards the normal. But here, we have some rather interesting consequences that I'm going to show to you right now. Here you go. Suppose that you are underwater and you have a laser source underwater, waterproof, laser source waterproof. And then you start playing with your laser, with your laser pen. First, you go ahead and illuminate the surface of the water from the bottom of the swimming pool at this angle. Okay? Well, what's going to happen? Light is going to refract away from the normal. That's the normal, right? Angle here is 1, angle here is a larger angle. And then you do something else. Okay, here you go. Air and glass. Second medium of lower refractive index. It looks like I repeat that, right? Okay, okay, let's start with this one. Okay, first instead of that angle, let's first you know, shine our laser beam at a 0 angle degree. Okay, what's going to happen is the following, You can use the Snell law equation, the equations for the Snell law. You're going to see the angle of refraction is going to be 0 degrees, okay? N1 sine of 0 degrees must be equal to 0, right? And N2 sine of theta 2 must be equal to 0 as well, right? Consequently, the angle of refraction is going to be 0 as well. But on the top of that, something else happens, okay? At this interface, light is going to be reflected as well. That's why I have this arrow pointing downwards, okay? So when we have this changing refractive index, not only we have the phenomenon of refraction, but we also have the phenomenon of reflection, which still obeys that law, the reflection. Now, theta of incidence is equal to theta of reflection. Okay. Now you change the angle, and you're going to have this light refracted and this other one reflected. In this case, angle of reflections is equal to the angle of incidence. And let me just erase this one here that we don't need. 1, 2, 3. Okay, so normal incidence, angular incidence. And now I can put my normal direction right in here. So you can see that the angle of refraction is larger than the angle of incidence. And this angle of reflection here is supposed to be equal to this other angle of reflection. Okay? Like that. Next. Okay, here you go. Now you go ahead and keep on changing the angle of incidence. When you keep on changing the angle of incidence, something interesting happens. Okay, the angle of refraction is going to keep on increasing until it comes to a point where the angle of refraction becomes 90 degrees. Okay, so in this case, you do not have any refraction whatsoever. No light is going to escape into the second medium. Okay? It happens for every angle above, for every incidence above this angle. This phenomenon has a name. It's called the phenomenon of total internal reflection. And it has several practical applications, especially in optical fibers. Okay, I work in this area, so I know very well how those things work. And I keep on repeating. Let's see here. Okay, I don't need that either, right? Let's erase it. Boom. Just keep on. And it is possible to find out what would be the minimum angle of incidence to achieve total internal reflection. Okay? Let's write that down here. When light propagates from a medium of lower refractive index to a second medium. No, wait a minute. a medium of higher refractive index to a second medium of lower refractive index, it is possible to achieve a condition that we call the total internal reflection. That we call total internal reflection. Light that is totally internally reflected, does not refract towards the next medium. Okay? The condition for total internal reflection is the following. The angle of refraction must be equal to what? Now at this point in time, you should have memorized that already. Equal to what? 90 degrees. Okay? And that should be gonna put it total internal reflection. Oh, by the way, greater or equal than 90 degrees. In order to achieve total internal reflection, the angle of incidence must be greater or equal than 90 degrees. At 90 degrees, this angle is called the critical. And by the way, we're talking, wait a minute. It's not greater than 90 degrees. It's equal, okay, for total internal reflection. Let's see. The angle of incidence is, no, the angle of refraction, oh man, there you go, it's equal to 90 degrees. Okay? When, when the angle of the angle of incidence for an angle of refraction of 9, the corresponding angle of incidence, let's put it this way, the corresponding angle of incidence is called the critical angle. And we are going to abbreviate that as theta sub c. Let me close the doors down there. It looks like a, give me some time, okay? My doors are banging here because of the wind. 1 minute. Okay, I'm back. I'm turning on the air conditioning too because I was feeling too hot here. Here you go. The corresponding angle of incidence is called the critical angle. Okay? So the situation is like that. We are going to use Snell's law to find out what's the equation for the critical angle is. So whenever, so whenever oh, okay, whenever theta of refraction is equal to 90 degrees, comma, theta of incidence is going to be equal to theta c. Okay? Theta of incidence is going to be equal to theta c. So now we can plug in these two values to obtain the critical angle. Okay, so here you go. I'm going just to repeat this Snell's law here. And now I'm going to substitute 90 degrees. And when I substitute 90 degrees here on the right side, I must change the other one to theta c. Okay? But don't forget, there must be a condition for that, right? The condition for total internal reflection to occur is the following. Refractive index of the first medium must be greater than refractive index of the second medium. If this inequality does not hold, then you do not have total internal reflection. Okay, now let's continue here. Sine at 90 degrees is equal to what? Everybody knows that sine of 90 degrees is 1, right? And now we can solve for the critical angle. Is going to be N2 divided by N1. Because N1 is greater than N2, this number is going to be less than 1, right? And then we have a real value for the angle theta. And now we have, all we have to do now is to invert this equation to obtain the critical angle, like that. Okay. And now we can start playing with those numbers for different indices of refraction. Okay. So let's do that. And then we're going to do here, see here, this one. Yeah, let's N1, N2. By the way, index of refraction doesn't have any units whatsoever, okay? It's a unitless unit. N1, N2. Yeah. N2. And what else? Let's say N1 is you're underwater, right? N2 is the air outside. We can now write down, find out what's the critical angle. And first with radians and then in degrees. Subscript like that. And then degrees here. I'm gonna put the symbol of degrees up superscript. Okay, so here you go. A sine, right? And 2, oops, what's happening here? Not trying, there's a problem with this formula. Not trying to have a form. Okay, let's see what's going on. Okay. And 2 over N1. That's the angle in radians. And then let's convert it to degrees. 48 degrees. When you achieve that, and let's see. Yeah, when you achieve the, and let's not forget, that's for a angle of refraction equal to 90 degrees, right? That's the critical angle. Above the critical angle, the light is going to be totally internally reflected. So it is as though as the interface, as the dielectric interface behaves as a mirror, as a regular mirror. Okay? And you can do for several other combinations of refractive index here. If you do all the way around, 1.133, you're going to see that you're not going to get any result because, the sign of theta has to be less than 1, right? Number, here you go. See, it doesn't calculate, doesn't compute. Doesn't compute because sine of theta cannot be greater than 1. Okay, I inverted N1 with N2. Let's write it down. Okay. Under total internal reflection, TIR, light propagates, Earth, IE, is an angle of incidence greater than the critical angle, comma, greater or equal than, right? Greater or equal than the critical angle. Light propagates, light reflects 100%, 100% at the interface between two media. In this case, water and air. Okay. Okay. For water and air, the critical angle is 48.75, 48.8 degrees, 48.8 degrees. Nope. 48.8 degrees, approximately. An important application of this effect is in optical fibers. Okay, so going back right here. So now suppose that you have a thick glass, or it can even be a pipe with water, right? A transparent pipe with water. And then you put a light source here inside. What's going to happen? Above the angle of above the critical angle, this light is going to propagate almost undiminished. Okay? Think about that. Okay, if light is propagated below this critical angle, what's going to happen? You know, you're going to lose some of the light to refraction, right? So eventually this component here, this reflected component, is going to become weaker and weaker. But if you illuminate, if your light is propagating at an angle of incidence that equal or greater than the angle, than the critical angle, then this light is going to propagate undiminished, okay? So you have 100% light reflected here, another 100% of the light reflected here, another 100% light reflected here, and so on. In real life, it's not exactly 100%, okay? But suppose that we have an ideal glass, because glasses can absorb light as well. It's not just a matter of losing light to refraction, but light can also be absorbed by the glass. But suppose that you have an ideal glass that doesn't absorb any light whatsoever. You can now propagate this light from one point to another one for very long distances. That's why people deploy optical fibers to carry telephonic signals underwater, okay? We're talking about thousands and thousands of kilometers of optical fibers, underwater optical fibers. By the same token that we still have today, right? Telephonic cables, electrical cables underwater. Now we are deploying optical fibers underwater to transmit telephonic signals for longer distances. Okay? Using optical fibers. And let's see if I can get you an illustration. Let's see. Of optical propagation in optical fibers. Let's see. I want to show you an actual drawing. Okay, here you go. There's an actual drawing. But wait a minute. I have something. Let's see if I have that in my site, right? I believe I showed that to you before. Okay, playing waveguide kits. Okay, here is when you illuminate the fiber on the side, right? See, we have some light reflected and you have some light refracted. See that? You can see that the angle of refraction is lower than the angle of reflection, or the angle of incidence. The angle of reflection is equal to the angle of incidence. Let's see if I have, okay. Now, what about here, right? Here is my special type of waveguide that I patented and invented. Notice that light is losing its intensity as it refracts towards the outside medium, right? Notice that something like that happened, right? As light propagates away from this plastic, the intensity of the trapped light decreases, okay? The same thing happens right in here, right? This first reflection, you lose some of the light, but because the angle of incidence keep on changing as I taper my waveguide, this is a tapered waveguide, right? Eventually, light comes to the point where it's going to be totally internally reflected. Believe it or not, nobody use this effect in optical fiber for side illumination. I managed to patent this thing that you're seeing right now. And people never managed to use this type of configuration because nobody knew about the side illumination. I have several patents on that. I have something around close to 70 patents on this type of effect that you see right in here. Okay? So do you see? Are those initial light rays that are incident at the interface at an angle lower than the critical angle, light, leaks out. But eventually, after several bounces, okay, and because of the fact that the angle of incidence keep on changing as the diameter of the fiber changes, eventually those light rays reach total internal reflection. So much that at this point here, there's no light leaking out, nor here, right? And nor here. And now we have a situation that this light can propagate for very, very long ways. Oh, do you see the light being reflected here? Okay. That's something that anybody can do with any laser pen, provided you have this special type of plastic that's sold out there. I tried to get the composition of this plastic. The guy refused to give me because he considered that a trade secret. I even contacted the technician that made that for him. They were not happy with me that I managed to find that guy. But I couldn't go any further because the technician that makes this thing to the guy for that guy has a exclusivity contract with the business that manufacture this with the business that market this plastic, okay, this special plastic. It just occurred to me, folks, that I was supposed to teach the lab, right? But I think it's better to continue lecturing today so I don't overwhelm you with the lab reports that we already have at lab 3, 4, and 5, right? So let's keep on lecturing in this subject. And someone is trying to come in. And I'm going to change the schedule here. And next Wednesday, we do lab number 5, okay? Let me see if I have infrared. Let's see the site of that industrial fiber optics. Industrial fiber optics. So I have this funny story. Those guys are in Tempe, Arizona. I met the president of this company, and he sells this special type of plastic. I tried to reproduce it, the special type of plastic in the lab there at LA Harbor, but I was not successful. Let's take a look. Infrared industrial fiber optics. No such product. Odd. No, fspoint.com. Why did he put this link here? So odd. Industrial fiber. No, that's not. That's their website. I-fiber optics. Okay. Now let's see the waveguide, optical fiber and cable, fiber optic connectors, LEDs, flexible light pipes, educational products, fiber optics, kits and projects, lasers, kits and projects, optical components, laser, kits and projects. Is that here? Let's see. Selection guide, laser kits and project. Let's try this one here. No, that's lasers. I don't want lasers. Specialized products. Must be this one here. They're teaching courses as well, huh? Speed of light apparatus, voice, see optical voice link kit. See that? They use light to transmit voice. Optical voice link, let's see, educational communication. I don't see it here. Fluorescent fiber kit, yeah, okay, so he's selling that as well. Optical sample kit, I don't see that product that I showed to you. Let's see. Specialized product, retractable optical fiber coupler, restricted light pipe. Must be this one here. No, it's not this one either. Is it possible they stopped selling it? optical fiber couplers, educational products, optical components. Oh, what a shame. I can't seem to find his fiber optical necks, flexible light pipes, cable assemblies. Okay, it looks like I'll have to check outside class. I thought I was going to be able to find it. I used to buy products from this guy. It's supposed to be here. Courses, technology modules, lasers, kits and project. Let's see, accessories. Fiber optic rod. Is it not? Let's see if it's this one. Especially for multi-technical for demonstrate the basic fiber optics, but they don't have the picture of. That's a shame. They used to have a picture just like mine, you know. They used to have a picture just like mine, but instead, you know, here in this case, I'm side illuminating, right? I'm also side illuminating here. This is the product that they sell, okay? But they used to have a picture showing laser being illuminating this end of the rod and the light propagating through it. 8, 9, yeah, okay. Optical fiber copper. Yeah. Let me try something else. Light propagation in a waveguide kit. Let's try. Yeah, that's not what I want. Well, too bad. I cannot show that to you now. They used to have it here. It looks like that they changed it there. Fiber assortment kit, fiber assortment deluxe. Experimenters kit. Fiber optic AD. Laser. Courses. Let's see if there is anything here in the courses. No, there's nothing here in the courses. Technology modules. Okay. I give up. I give up. Let's make sure that I'm recording, right? Pause. Yeah, we're recording. So let's go back here to our Snell's law, total internal reflection. So we did 26.1, 26.2, 26.3. Okay. And that's the one that's okay. Let's copy and paste it here, right? We did everything that is in bold face. We are going to skip, for now, we're going to skip that. Skip for now. And you need to know what dispersion of light is. Okay, so what's dispersion of light? Yeah, I'm back here to my wave API kit. Okay. Shot. Yeah. Okay, so let's talk about dispersion now. Dispersion of light. You have to know what dispersion is. What is dispersion, right? Dispersion. Okay, so I have to explain to you that material with a given optical density, materials with a given optical density exhibit optical dispersive properties. Okay, what's dispersion, right? What is dispersion? Okay. Okay, the answer is very simple. Light. Consider, consider a given optical material of refractive index n equal to 1.5, okay? Dispersion is the property of light of different wavelengths, fill, right? Fill. A different refractive index, even when it propagates along the same material, right? So let's say, I'm going to give an example. I'm going to give you an example, okay? If blue light, the wavelength 400 nanometers, right? Let's say 400 nanometer wavelengths. Feels experience, right? Field now experiences a refractive index of 1.5 in the above medium, comma, red light at, let's say, a wavelength 630 nanometers wavelength will experience a different refractive index, say, 1.48. Okay? In general, the higher the wavelengths, the lower the refractive index. Okay? Do you picture that? Okay? That's why we can see the rainbow. The rainbow is a practical example of optical dispersion. When white light goes through the droplets of rain, right? White light is made of all sorts of wavelengths. It's made of red wavelengths, blue wavelengths, yellow wavelengths, and so on. Each of those wavelengths are going to refract differently because the material will have a different refractive index for different wavelengths. And because of that, the refraction is going to be different for every wavelength. And we'll be able to split the white light in several of its colored components. That's why we can see the rainbow. Okay? So mathematically, optical dispersion can be written down in terms of the refractive index as a function of the wavelengths. Okay? So here you go. It's something like that, roughly inversely proportional to the wavelengths. Okay? The refractive index is a function of the wavelengths, and it's roughly inversely proportional to the wavelengths. So in real life, all optical materials do not have a single wavelength. They have multiple wavelengths that varies according, that doesn't have a single index of refraction, okay? Opticals, but it does not have a single index of refraction, refractive index. Instead, they have multiple refractive index that depends on the wavelength of the light. That's what dispersion is all about. You know, dispersion is the refractive index change of a material with the wavelengths of light, of the light. Okay, that's what dispersion is. And let's take a look at some interesting. Oh, right in here, I have a drawing right in here. You go. This one. Okay, so you get, suppose that you have a white light, a white laser. They are trying to develop those things, right, and start to sell out there. So highly collimated source is incident right in here at this interface. And then what's going to happen? Because the blue wavelength has a lower wavelength, it's going to see a higher refractive index. It's going to feel a higher refractive index. That's why it is, you know, its path is switched, right? By a higher angle. By a higher angle. Okay, higher angle, no, a lower angle. And then, you know, you have all those different wavelengths that is split, that you can discern, right? That you can break down according to the optical dispersion property of this medium. Let's see if we have anything here in your book. Index of refraction, total dispersion. Prism, okay, right in here. Okay, so incident light, we have this normal here, right? And the blue wavelengths is the path of the blue wavelengths is bent more strongly than the path of the red light. Okay, so here you go. Here's this table. So at 660 nanometers is the red wavelengths. That's the refractive index that corresponds to the red wavelength of a given material, okay? As we go towards the blue, the refractive index increases, right? The lower the wavelengths, the higher the refractive index. That's what dispersion is all about. Okay. And here you go. Here's the light being dispersed by a water droplet. That's what ends up causing the rainbow that we see. (11:58), and then the next topic is going to be on lenses. I want to take a break again. Okay, break from 11:58 to 12:13 p.m. Okay, any questions about that? So remember this phenomenon of dispersion. Light dispersion, formation, spherical lens, dispersion of light. We are writing here. And now we are ready to look into spherical lenses. So I see you in 15 minutes. Okay, I'm back here. So folks, sorry I'm a little bit late here, and let's continue. More students coming in. Okay. Let me give you an example of real life. I'm going to give you a real life example. I'm going to give you a real life example of optical dispersion. There is a company called Shot Glasses. This is a German company. This is a German company that manufactures optical glasses, high quality optical glasses. Okay? I used to buy their glass when I work at NASA, okay? When in another lifetime, right? In another universe, when I used to work at NASA, I bought several glasses from them to manufacture my optical fibers. Okay, and here you go. Let's see. I have one of their website. They link to their website. Let's see if I can get change cookie. Yes, I agree. Right? Quality assurance. Shot optical glasses is a well-renowned company in the optical field. They have been around for at least 100 years. And it's a German company. They were established there in Germany. And I heard this story from a colleague of mine that during the World War, when the Russians and the Americans, the British and the French were taking over Germany, right? At the end of the war, Germany was divided into 4 areas of influence. One for the Russians, another for the Americans, another for the French, and the other one for the British. Okay, so the guys from Shot Glass were during the final days of the war, right? The guys from Shot Glass was worried that they could be bombed into non-existence by the Allied troops. So they were concerned, how can we keep all this technical knowledge that we accumulated during all those years? And most of this technical knowledge, of course, was a trade secret for them. And then they came with the idea, okay, let's go to Japan. Let's set up a factory there in Japan. And they transfer some of their operations to Japan. Okay, that's the story that I was told. Here in the site, they have data sheets of their glasses, including data sheet on the dispersion of many of their glasses. See, they're all data sheets, very detailed data sheets documenting the refractive index of different optical glasses according to their wavelengths. Okay? See pocket catalog. In the past, those things were all in a bunch of papers, piece of papers, right? At that time, we didn't have, when I was at NASA, right? We still didn't have the internet like it is today. So at the time, Shot was to give away their technical data in with several pages of data of their glasses. So you can see, technical information, test report, temperature coefficient of refractive index, okay? See that? Even the refractive index also changes the temperature of the glass, okay? Stress in optical glass. See, look at the extensive, refractive index and dispersion. Look at the extensive data that they have collected. Fluorescence of optical glasses, transmittance of optical glasses, okay? Bending strengths, right? But we're interested in the refractive index and dispersion of their optical glasses. Let's see if we can download this data sheet so you can have a better idea how the refractive index change. Refractive index, wavelength dependence of refractive index. Okay, here goes. You should recognize this law here, right? And you should recognize this relationship as well. The speed of the light divided by the speed of the light in the material. The speed of the light in vacuum divided by the speed of the light in the material. And here is Snell's law. Technical information, okay. Wavelengths, refractive index. Okay, you can see that the refractive index changes with the wavelengths. Okay, so let's see, the longer refractive index, smaller wavelengths. Okay, longer let's see, longer the wavelengths, the smaller the refractive index. Okay, that's what it is. So you start here around 2 point whatever, right, at this funny wavelength, and then it goes down. Like I said, for the sake of this course, it's okay to believe that the refractive index decreases with the wavelength. It's okay, but just for the sake of the course, of this course. In real life, it's a little bit more complex than that, okay? As you can see, there is this other region here that's not for the interest of this course, in which the refractive index increases with the wavelengths, okay? That's the region that we call region of anomalous dispersion. Okay, but you should be, concerned only about this region of normal dispersion. Okay, so what we're teaching here is not everything that you're supposed to know, that you should know. Okay, you're supposed to know only what I'm telling you here. The region of this anomalous dispersion, forget about that. Don't worry about that. Let's see here. Refractive index and dispersion in glasses. I want to see if you have the wavelengths here. Okay, that's VD. Okay, we don't want to look into that. I want to see a table that they have for their different glasses. Wavelengths, designation element. Okay, each of the wavelengths that you have here correspond to one of the lines of a given molecule. Okay, the mercury lamps, they emit wavelengths at they emit light at different wavelengths. So here's the infrared region, right? 1,970 nanometers or 1.97 microns. Okay, red helium line Okay, red hydrogen line, that's the wavelengths. So the hydrogen gas emit wavelengths at this in this wavelengths, and so on. You have all sorts of wavelengths that they measure. They took the measurement for the dispersion. They use all those different wavelengths. Think about that. You know, this is a major operation, folks. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. How many wavelengths they have, right? 17, right? Let's stop on 17. Let's see. 17 here, 17, 18, 19, 20, 21, 22, 23. 23 different wavelengths. They're measuring the dispersion of their glasses for 23 different wavelengths. Okay? And here go. That's a annealing rate. You don't want to know about that. Refractive index and dispersion. Let's see if we can get that. I'm looking for actual data for their glasses. It's not here. Okay, it must be in another one. Let's check. Let's check another one. Must be in another one. Let's take a look. Optical glass data sheet collection. Maybe this one. Okay, you can see that it's a very extensive document, right? It's a PDF file. Those are all the glasses that they have, all sorts of glasses, different chemical compositions, okay? Think about that. They managed to manufacture all that stuff and commercialize too, not just manufacturing, but it's commercialization as well, which is far more difficult. Okay, here you go. That's the table I was looking for. Okay, refractive index and wavelengths for this specific glass. Okay, in the infrared is 1.46. As we go lower and lower in the wavelengths, the refractive index increases, right? Just like I said, inversely proportional to the wavelengths. The refractive index is inversely proportional to the wavelengths. But let's not forget that was the region, what we call the region of normal dispersion. Okay? And okay. And then you have other quantities that they're measuring as well, right? Temperature coefficient, this one is internal transmission, but we are concerned about the refractive index because of the dispersion. I want to, okay, here's another glass, okay? NFK5, 146 at longer wavelengths, 152 at the shortest wavelength. You see, they mostly are in the 1.5 refractive index range. Glasses are mostly 1.5 refractive index range. Okay, so if you go through that, you would see that, you know, they all increases. The refractive index decreases with the wavelengths or increases with the frequency, right? Frequency of the light. 1.5 at the infrared, 2325 nanometers, 1.55. Okay, increase it by 0.05 in refractive index. When so here you go. This is a more exotic glass because it has a refractive index around 1.6. It's difficult to find materials that has this high refractive index. 1.59 all the way up to 166. Okay, so that's what dispersion is. Did you get an idea what dispersion is? Let's see if they have 1.7. I have always been curious, very curious about high refractive index glasses. Let's see if they have. One is 1.7. Doesn't look like, right? Doesn't look like. So far, those numbers are not refractive index. Oh yeah, they do have it. See that? This fancy glass here, NLAK8. varies anywhere between 1.67 all the way up to 1.75. Let's see, 1.8. 1.8, I don't think you're gonna find any glass like that. Those 1.8 that you are finding is not refractive index, it's some other measurements. I'm gonna give a link for this document in case you want to know more about it. Yeah. You see how extensive this document is? Let me see, it looks like it has 150 pages, more or less. 137 pages, okay? Oh, here you go, this glass has 1.8 refractive index. LAK 33B, okay? But depends on the wavelengths, of course. 1.8 at 334, okay, 334 is already the ultraviolet region. And so on, right? So let me copy this link here into my notes. For dispersion tables of optical glasses. Check the website of shot glass. Okay, you go like that. Let's see if I can go there. This one, data sheet collection, right? Just the very first one. Just the very first one. That document on dispersion that we saw is just some technical information of what are the wavelengths that they use and how they use what was the experimental procedure, right? To measure the dispersion. And so it's in there. Let's go close that thing. And oh, they also have an Excel table, okay? They also have an Excel table. Concentrate on the following links: optical glass collection data sheet, right? The very first one at the top. And then they also have an overview in Excel table. They make everything simple for you, right? It's amazing. And now you're right, we're ready to start spherical lenses. We have 15 more minutes to go. And spherical lenses. By the same token that we have spherical mirrors, we also have spherical lenses, okay? And those are the simplest type of lens. We will introduce the very basic idea of a thin spherical lens, okay? Thin is defined in terms of the diameter d of the lens, where the thickness of the lens is much less than the diameter. So this is an approximation. This theory that I'm presenting to you is an approximation. If you want to know what happens for secret lenses behaves, the theoretical treatment of secret lenses is far more complex than the theoretical treatment of thin lenses, right? And then here we present only the treatment of thin lenses. Is a very good approximation for real life lenses, for most, right? For most real life lenses. And by the way, this section is rather similar to the one that we presented for mirrors. It's amazing. Those are two different devices, but the equations used are rather similar, okay? Although it's a little bit more involved, because now we are dealing with a lens. We're dealing with two optical surfaces, two sides of the glass. The mirror used only one side of the glass, right? But a lens used the both sides of the glass. That's why it's a little bit more complicated. The device is different, light behaves differently, but the final formulas are exactly the same. Are the same. Okay, and that can be proven as well. And I have already told you about light rays that travel parallel to the axis of the device, of the optical device, parallel light rays that travel parallel to the, to the optical axis, either of the lens, of the mirror or the lens, okay? But there is another useful way of producing a parallel light ray, okay? A parallel light ray is obtained when the source is very far away from the lens or the mirror. That's how, for instance, light coming from the sun, we can say that is collimated because the sun is so far away, that each light ray of the sun that arrives here, they are almost parallel to each other. And I can explain that very easily. I can explain it very easily using my illustration here, okay? I'm going to picture here a large source. Let's say that's the sun, right? And the light from the sun comes perpendicular to the surface of the sun. The light all radiates away, just like the electric field. One light ray, another light ray, another light ray. Do you see that? Another light ray, another light ray. Okay? If you are sitting right in here, okay, at this point here, you can see that all those light rays that reaches you, they are not parallel at all, right? That's because you are very close to the sun. This light ray makes an angle with this light ray, and this light ray, and so on. Things change when the source is very small or a large source is very far away from you. The situation changes, right? When the source is very small and you're also very far away from that source. And even more, especially planet Earth, right? Planet Earth is very far away and corresponds to a very small cross section right here. And here you go. That's the sun. I want to get this light rays since I already have them. I'm going to line them up with the sun that's very far away from the Earth. That's a very nice way. Okay, because the Earth is a very small planet compared to the sun, it will not be able to collect those light rays that's radiating away, right? But it will be able to be exposed to this light ray, let's say. Let me move it a little bit higher. Okay. And let me get also better. And I'm even going to bring to the front. And then here you go. Here's another light ray. Look at the angle that you have here. It's a very small angle. So because this angle is so small, it's almost 0 degrees. we can approximately say that the light rays are parallel. The light rays that reach the Earth from the sun are parallel to each other, okay? That's why, a very distant source can be said to emit light rays that are collimated. Okay? That's the idea. And let's not forget, okay? I am exaggerating on the size of the Earth. The Earth is not that big. The Earth is smaller than that. It's much smaller than that, because if I'm making the sun this size, the Earth is, man, I won't even be able to see the Earth here, right? I'm exaggerating. Let's write that down. Okay. Parallel light rays are rays that come from an object that's very far away from the lens or from the object. Let's put from the object that's capturing the light. It's said to be parallel to the principal axis of your lens or mirror, right? The light rays of the stars as well as the moon, etc. The further a light source is from you, the more collimated light ray will be. Also, likewise, the smaller is the instrument, the smaller the instrument that's collecting, the smaller the instrument who is collecting the light from this distant source, the more parallel the light rays are. Okay? Depends not just on the distance, but also depends on the size of your instrument that's capturing the light. And the instrument can be, for instance, a detector, a photodetector. Can be a photodetector is an object that measures the light intensity, okay? Your telescope, your lens, your mirror, okay? How do you judge whether an object is far away from the lens or not? Okay, a very good way to judge, to make this judgment, to make this call, is to compare the position of the object with the focal distance of your mirror or lens. Okay, a lens also has a focal distance that we are going to cover. And much greater should be what? D naught greater than 10 times the focal distance. If this condition is satisfied, we can state that the light rays are almost parallel to the principal axis of the optical device. There are 5 different types of lenses. Okay, don't forget lenses have 2 optical surfaces. Okay, the one type of lens is the planar convex lens. Let's see if I have a drawing here for that. Okay, here you go. Here's how we, don't forget the spherical, we're dealing with the spherical lenses, right? How do we form a spherical lens? Both surfaces of the lens are defined in terms of a sphere. Here's the section of one of the sphere, right? And here is the section of another sphere. But this sphere is funny. This is a funny sphere. It has a radius of curvature that's equal to infinity. It's a very large radius of curvature. That's a planar convex lens. Okay? Planar convex lens. And that's the one. We call it positive. Positive lens. Every lens that has a convex surface is going to be a positive lens. Okay, here you go, planar convex lens. Here's the axis, the principal axis of the lens. Here is the parallel light ray comes from a very far source. And then how is this light going to behave, right? Let's take a look, here you go. I'm going to put another frame in this movie that I'm going to play to you. Okay, so here you go. The light ray comes from far away, coming from far away. The light ray is arriving the lens. Whenever it's incident at that first planar surface, okay, is incidence at an angle of incidence equal to 0 degrees. So it's not going to be deflected. Make sense? 0 degrees incidence, 0 degrees refraction. And that's what you have right in here. But then when it reaches this other surface, the second surface that has a curvature, now we do have an angle of incidence in this curvature, right? Here you go. Here's the normal. Here's the tangent, the plane that's tangent to the lens, and here is the direction that's perpendicular to that tangential plane. We have this angle of incidence. We have this angle of incidence, and you should expect that the angle of refraction is going to become greater because now the light is traveling from one medium of high optical density to another medium of lower optical density. Make sense? Right? So here you go. And that's not the direction of the light ray. That's just the direction of the through direction with no refraction, okay? The actual direction of refraction is going to be this one that you see right here. I put this one just as a reference. I put this one just like a reference for me, okay? Away from the normal, light is refracting away from the normal. That's how a lens works, okay? Here you go. This point where the light ray intersects the main axis of the lens is called the focal point. And then we can have the same thing for the other light rays that travel parallel to the axis of the lens, okay? We have this light ray here. It's gonna be deflected towards the focal point as well. Okay, 12:50. Okay, we run out of time. And that's what I want to show you for now. We are going to do that. Next time, we're going to elaborate a little bit on this path of the light rays, okay? So let's stop now, and I'll have office hours. If you want to hang around and ask some questions, let me know. You're welcome.
Thanks, Professor.
Welcome. Let's stop sharing. Stop recording.